Today's topic is transforms. You are familiar with the Laplace transform from earlier courses. So this topic, which is moment-generating functions for random variables, will heavily use those skills, but you're not absolutely required to have those skills. Now, last time we worked with variances a lot, and we talked about the variance being a second-order characteristic for a distribution. Particularly, it's related to the second moment. The variance for a random variable x is defined as the difference of the from the second moment of the first moment. Meaning, remember, variance of x for any random variable x is the expectation of x squared minus expected x squared. Now, what is expectation of x squared? This is the second moment for the random variable x. What is the expectation of x? Expectation is the first moment. In general, the nth moment of a random variable is the expectation of x raised to the power n. Now, the transform that we'll learn today is also called a moment-generating function. It's a function that we can use to generate nth moments for any n. Okay, specifically, the transform or the moment-generating function MGF of a random variable x is defined as m sub x of x s being equal to the expectation of e to the power s times x. Now, let's think about this expression. It's an expectation of e to the sx. What is random here in this expectation? X is random. So the expectation is over the distribution of x. So once you do this expectation, what is this a function of? Once you compute the expectation over x, it's not a function of x anymore. It's just a function of the parameter s. Okay? So this is a function parameterized by s. It's just like a Laplace transform or a z transform, as we'll see. So in the discrete case, mx of s, since it's the expectation, it's going to be a summation of this function e to the sx multiplied by the Pmf p sub x of x. So those of you who have seen the z transform will recognize this as a z transform, where z is e to the s. It's not important, okay? So in discrete case, this is just an expectation which we know how to compute. In the continuous case, it's an expectation, again, which we know how to compute, e to the sx times the density fx of x dx, integrated over all real numbers. We know how to compute expectations, so computations of moment-generating functions is not really difficult. So let's exercise a little bit on this by first computing the moment-generating function of a Poisson random variable. So let's assume x is Poisson. How many parameters does a Poisson random variable have? Just one, and that's the rate. Okay? Poisson with rate lambda. So we need to compute the expected value of e to the sx. Is this going to be an integral or a summation? A summation, because Poisson is a discrete random variable. So this is going to be summation. Okay, what is the Poisson Pmf? We need to write here the Poisson Pmf p sub x of k. This is the probability that x is equal to k, and it is given by lambda to the k e to the minus lambda over k factorial. For which values of k? 0 to infinity. Positive integers. So k from 0 to infinity. Okay? Or non-negative integers to be correct. Now, let's keep this, before we make px of k specific, let's leave this general from minus infinity to infinity. And then, this is true for k bigger than or equal to 0. And then we substitute in the PMF. 0 to infinity, e to the sk, lambda to the k, e to the minus lambda over k factorial. What do we do? Well, first of all, we realize that this e to the minus lambda here has no k dependence. We can get it out of the summation, e to the minus lambda, summation, lambda e to the s raised to the power k divided by k factorial, k from 0 to infinity. Any ideas? At this point, you may realize that summation k from 0 to infinity, a to the k over k factorial is the expansion of e to the a. So, using this, this is equal to e to the a, where a is the lambda e to the s. And we can just write the whole thing as e to the minus lambda e to the lambda e to the s. So putting the exponents together, we get e to the lambda e to the s minus 1. Okay? So this is, it turns out that this is the moment generating function mx of s, where x is a Poisson random variable with parameter lambda. Okay? Any questions? So let me ask you a question. When I plug in s equals 0 in the moment generating function, what should I get? S equals 0, it's the expectation of e to the 0. In other words, the expectation of 1. Exactly, so I should get 1. So let's check if this satisfies that. Plug in s equals 0, this is 1. 1 minus 1 is 0, so we have e to the 0, which is 1. Checks with that. Okay. Any questions? So let's switch to the next exercise. The next one is finding the moment generating function of an exponential. So let x be exponential now, again with a parameter lambda. Let's not confuse this lambda with that lambda, although they are very intimately related, as you'll see when we've studied the Poisson process. But this x is a discrete random variable. This x is an exponential random variable. Remember the exponential? How do you remember the exponential? The probability that x exceeds a value decays exponentially at rate lambda. Okay? And from that, well, let me repeat that. fx of x, which is the probability that x is less than or equal to x, which is the 1 minus the probability that x is bigger than x. Well, this is the one that decays exponentially. This is e to the minus lambda x. So the CDF becomes 1 minus e to the lambda x. And the PDF is a derivative of this, which is lambda e to the minus lambda x. Okay? So now we need to compute the moment generating function. How do we do that? It's the expectation of e to the sx, which is an integral of e to the sx fx of x dx from negative infinity to positive infinity. Okay, so plug in, well, this is of course valid for x is bigger than or equal to 0. So plug in the density, we get 0 to infinity, e to the sx, e to the minus lambda x dx with a lambda multiplier at the front. So, what is this integral? Is it always finite? Well, I have the integral of e to the s minus lambda x dx. Does this integral always converge? It converges when the coefficient of x here is negative, right? Otherwise, it's an increasing exponential and I can't integrate it over all r because it would blow up, okay? So only when this coefficient is negative can I integrate it. So basically, I'm going to say here, when s is less than lambda, for s less than lambda, this is negative, and the integral evaluates to 1 over s minus lambda. So it's lambda over lambda minus s, right? Because it's 1 over s minus lambda times e to the s minus lambda. Plug in infinity, you get negative, you get 0. Plug in 0, you get 1 with a negative sign, so you get this. Okay, so this is the moment generating function of an exponential. It's valid, let me repeat, for values of s that are less than lambda. If you know the Laplace transform, you will recognize this expression as the Laplace transform of this function, the PDF, except in the Laplace transform we usually use a negative s here. Okay? So remember, in the Laplace transform there's a region of convergence. So this expression is valid only when s is less than lambda. So it converges only when s is less than lambda. It's not really important for our purposes, okay? In probability, basically we're doing only a 2-hour lecture on this, and it's not really that important, the mathematical details of this. You just need to be able to use transforms to do a number of things, to make a number of things easier, which examples of which we'll see today. Any questions? Okay. The next exercise is computing the moment generating function of a linear function of a random variable when we know the moment generating function of the original random variable. So suppose the random variable x has a moment generating function mx of s. Okay? Define y as ax plus b. I obtain y by linearly scaling x. What is my of s in terms of mx of s? That's very easy. You'll see. We're collecting the benefits of learning properties of expectation here. So basically, my of s, write the definition. It's the expectation of e to the sy. Plug in y in terms of s, x, e to the s times ax plus b. What do you see? I have e to the ax times e to the sb. E to the sb is a constant, comes out of the expectation as a factor. I have e to the as, or sa, if you want, sax. But this is nothing but the moment generating function of x defined at the parameter value as. Okay, so I can reach this general result, fill in the place of this question mark here, e to the SB mx of as. This is something that will be useful, for example, when we show, here, this gives another way, easy way of showing that, for example, when you scale a Gaussian linearly, you get another Gaussian. Okay, what's next? Yes, please. We're computing the moment generating function of various distributions. We will use the moment generating functions to do a number of things. For example, generate moments. Right? That's why they're called moment generating functions. And to, for example, get rid of the need to do a convolution, as we'll show now. When you add two random variables that are independent, the PDF of the sum, remember, is the convolution of the PDFs. But the transform of the sum is the product of the transforms, as we will see. Okay? So the moment generating function, it has certain uses. And right now we define the moment generating function, and we are computing the moment generating functions of a certain number of random variables. Okay, the next one is the Gaussian. So Gaussian with mean, mu, variance, sigma squared. So that's going to be tough because it involves an integral which I'm going to have to do manipulations on, and I'm going to need your help to keep track of things. Okay? Are we ready? So let's see. X is normal with mean, mu, variance, sigma squared. I want to compute mx of s, which is the integral. You tell me the limits of integration. The Gaussian is spread over the whole real line. So negative infinity to positive infinity. E to the sx times 1 over square root 2 pi sigma squared e to the minus x minus mu squared over 2 sigma squared dx. Very nice. So what do we do? What we do is we'll try to get another Gaussian PDF out of this. Okay, we'll make use of our knowledge that the Gaussian PDF integrates to 1. That's what we'll do. Okay, so let me put the two exponentials together. So I have e to the sx minus x squared plus 2x mu minus mu squared. Okay? We all need to be very careful so that I don't make a mistake while doing this. Okay? So I'd like you to watch, or I'd like you to check to make sure what we're doing is right at every step. So what do you see here? A quadratic. Maybe I can collect the terms such that I will make it, I will complete to a perfect square. Okay, that involves all x terms. Okay, and I can throw the remaining on the outside. Okay, so let's complete this to a square. Well, I have x squared here. I have sx minus 2 mu x and mu squared. So how about I write this as, let me take another color. I can write this as negative x squared plus 2 s over 2 plus mu x, right? What? Yes, please.
Şurada SX'i o kağıdın içinde yazmak
Very nice. Thank you. So that's exactly what I meant. Thank you. So we need to multiply here by 2 sigma squared, right? 2 sigma squared. Okay. So I have negative x squared plus 2. Let me write here. 2 times 2 times x mu plus sigma squared sx. Okay? Right? 2 times x mu plus sigma squared sx minus mu squared. Okay? That's the that's what I have here, divided by, of course, 2 sigma squared. In other words, this exponent is equal to negative x squared plus 2x times mu plus sigma squared s, okay, minus, or let's say plus this, here I should have, yes, here I should have a negative sign. Very nice. Plus the square of negative, okay, mu plus sigma squared s, right? Plus some additional terms divided by 2 sigma squared. Okay? I'm trying to complete it to a square, so provided we find the additional terms, we're done, right? Because I have x squared plus 2x times this plus the square of this. Okay? So the square of this would involve mu squared plus, maybe let's get the negative out here just to make sure they look the same. Okay, mu squared plus 2 sigma squared s squared. So let's put here negative 2 sigma squared s squared. Plus 2 mu sigma squared s. So I plug in here 2 mu sigma squared s. What do you think? Sigma to the 4, you're right. Okay. Let's check. Let's check. I have all this with the right sign. And then I have here, from here I get negative mu squared plus 2 mu sigma squared s plus sigma to the 4 s squared. And from here I get negative 2 sigma to the 4 s squared minus 2 mu sigma squared s. And when I cancel the terms, I get, let's see, sigma to the 4, sigma to the 4 s squared term should not come with a 2, of course, and should come with a plus. In that case, it would end up canceling this term. Very nice. And then the 2 mu, this should come with a plus, right? These two would cancel each other, and then we would be left with a negative mu squared as desired. Okay? So, are you checking? Where? Okay. I have here mu squared. Okay, and right. So this is not necessary, you're saying, which is okay. So let's make these negative. These should be positive. Anyway, let's move on. Let's move on. And let's switch to the bigger expression. We have here x in the exponent. We have finally the square of x plus or x minus mu plus sigma squared s. Okay. Plus some additional terms. Let me write the additional term. Well, I can move the additional terms over to this side because they have no x dependence. Let's move the additional terms as e to the negative sigma to the 4 s squared plus 2 mu sigma squared s over 2 sigma squared. Okay? And eventually, what happens? What is this integral? Huh? This is the integral of a Gaussian density, right? Whose mean has changed. So that's going to be 1. And here, basically, so since this is 1, I'm left with... Do you see that this is a Gaussian density with mean as this? Huh? So I have e to the sigma squared s. Wait a second. E to the sigma squared s plus mu s. And somehow the negative should go. Wait. E to the sigma squared over 2 s squared plus mu s. Okay. So here's what's your question again? Right. Now, I try to manipulate this to get it looking like a Gaussian density. Okay? So, to do that, in order to do that, I needed to complete this to a perfect square. We completed it to the perfect square of this, x minus mu plus sigma squared s. Okay? So, this is nothing but the PDF of a Gaussian, okay, whose mean is at this value. Okay? And integrating the PDF of a Gaussian gives me 1. And as a coefficient, I get the remaining terms out of the integral. And those remaining terms, provided we didn't make any computation errors, look like this. So let me rewrite this. E to the mu s plus sigma squared s squared over 2, or let's put s here, e to the s times, or okay, let's keep the s squared term in the front, sigma squared over 2s squared. Okay? We can check later if this is correct or we made an algebraic error. Okay, so this is a good exercise for you to do on your own, repeat on your own as well. What's next? Now, oops. The next exercise is an application of this result together with the linearity result that we proved earlier. Okay? So using the moment generating function of the Gaussian and the property we just proved about the transform of a linear function of a random variable show that a linear function of a Gaussian random variable is also Gaussian. Okay? So here's a setup. X is normal with mean mu, variance sigma squared. Y is ax plus b. So what is my of s? My of s, as we showed, is e to the sb times mx evaluated at a times s. Right? We just showed this. Now, e to the sb times mx of as. We need to plug in as instead of s. E to the mu as plus sigma squared over 2 a squared s squared, right? So what happens? Let's multiply out and collect the terms. E to the mu a plus b s, okay, plus sigma squared, or maybe a squared sigma squared over 2s squared. What is this? This is in exactly this form. It's a Gaussian with the mean equal to a mu plus b and variance equal to a squared times sigma squared, which is a result that we knew from earlier computations. So therefore, well, I'm saying therefore, although I haven't argued for you that there's a one-to-one correspondence between moment generating functions and densities. However, it is true, it's sort of beyond our scope, that if you know the moment generating function of a random variable, you know the distribution. So the transform uniquely determines the distribution. So therefore, y, we conclude, is normal with mean a mu plus b and variance a squared sigma squared. Any questions? Okay, now is the time to address why this function or this transform is called the moment generating function. It's called the moment generating function, not because it generates beautiful moments between you and your friends, but it generates the nth moment expected value x to the n. Okay? Expected value of x to the n can indeed be found by differentiating mx of s n times and plugging in s equals 0. Okay? So rather than do a nasty integral, okay, somebody has taken the integral for you, example here. Okay? So what you do is differentiate that n times. Okay? Differentiation tends to be easier than integration. And then plug in s equals 0. Now let's prove that this is true. That's not going to be very hard. Let me erase my miserable computations here. Okay, so let's see. I have expected value of e to the sx, and I want to go and differentiate this n times with respect to the parameter s. So let's make x bigger. I want to differentiate this. Okay. So now I will assume that I can exchange the order of expectation and differentiation. Why? Because the expectation in the PDF case is an integral. And if you assume that the integral converges, which we have to assume for the nth moment to exist anyway, then I can change the order of integration and differentiation. Similarly, if it's a summation, there's no problem if the summation converges. So basically, let's move the differentiation inside. Okay. And then I get, what is the nth derivative of this? It's going to be x to the n e to the sx. Okay, because I'm differentiating with respect to s. Now plug in s equals 0, I get the expectation of x to the n. So if you find this a little fishy, please write it for discrete and the continuous case separately, and convince yourself that that works out. Okay, so using this, let's determine the mean and the variance of the exponential. So example, exponential. X is exponential with rate lambda. We just showed that mx of s is lambda over lambda minus s, provided s is less than lambda. Okay? So let's differentiate once to get the mean. D by ds mx of s is nothing but lambda over lambda minus s squared. The negative sign is cancelled because there's a negative sign here. Okay? And then evaluate this at s equals 0. It gives us what? 1 over lambda, which should be the mean of the exponential. Is it true? Yes. We remember this from our previous analysis of the exponential distribution. The exponential distribution decays with the rate lambda. Its mean is proportional to 1 over lambda. Its mean is exactly equal to 1 over lambda, actually. Okay, how about differentiate once more? D squared by ds squared of 1 over lambda minus s, lambda over lambda minus s, is d by ds of lambda over lambda minus s squared, and we have 2 lambda over lambda minus s cubed. Let's compute the value of this at s equals 0. It gives us 2 lambda over lambda cubed. In other words, 2 over lambda squared. What is this? This is the second moment. This is the expectation of x squared, because I am computing the second derivative of the moment generating function at the value s equals 0. This is the second moment. So what is the variance? Variance of x is expected x squared, which is the second moment, minus the first moment squared, which is 2 over lambda squared minus the square of 1 over lambda, which is 1 over lambda squared, as we already knew. Any questions? Okay. So we computed the mean and the variance of an exponential random variable. As I said, let me repeat. The transform of a random variable x uniquely determines the distribution. And when there is a PDF, it determines the PDF. One can always find, potentially, the PDF or the PMF from mx of s. So we'll usually, in this course, we're not going to go into major inversions, but we'll usually invert transforms by pattern matching. So we'll recognize a certain function of s as related to the transform of a PDF that we know. So as an example, let's look at the mixture of two exponentials here. So here's the problem. The length in kilobytes of IP packets received at a switch, okay, are with 80% probability exponentially distributed with mean 10 kilobytes and with 20% probability exponentially distributed with mean 100. Determine the moment generating function of the length of a randomly selected packet. Randomly selected means selected uniformly at random. Yes, please. We won't. So this is what is this note, I guess, is not complete. It's about a continuous random. This applies to a continuous random variable. We'll do an example in the next hour showing how we can go from a moment generating function of a discrete random variable to the PMF itself. Okay. Right now, let's focus on this example. So the example setup is the file length, the packet length is either exponential with a small mean, 10 kilobytes, or exponential with a large mean, 100 kilobytes. Determine the moment generating function of a randomly selected packet. So a randomly selected packet is with probability 0.8 coming from the small packets group, packets that are likely to be small. And with 20% probability is coming from the large packets group. Okay. We need to compute the expected value of e to the sx. Here we'll use our total expectation theorem skills. Okay. So this is with probability 0.8 expected value of e to the sx1, okay, where x1 is exponentially distributed at rate lambda equals 1 over 10. Okay? And with probability 0.2, it's the expectation of e to the sx2. Right? Where x2 is exponential at rate lambda equals, lambda 2 equals 1 over 100. Okay? In other words, you can see this as the expected value of this function is 0.8 times expected value of this function given event A. Event A is the packet I selected is from the small packets group, plus 0.2 times the expectation of this function given A complement. A complement is the event that the packet I selected comes from the large packets group. Okay, so let's compute this. I get 0.8 times lambda over lambda minus s, remember, and my lambda is 0.1. 0.1 over 0.1 minus s plus 0.2 times 0.01, which is 1 over 100, over 0.01 minus s. Okay? That's it. I don't need to further simplify this. This is the moment generating function of my packet length x. It's the mixture of two exponential distributions. So let's think of this the reverse way. If someone gives you mx of s, the moment generating function, as, let's see, 0.4 over 5 times 0.1 minus s plus 0.002, no, let's say 0.01 divided by 5 times 0.01 minus s. What does this make you think? This makes me think that perhaps this random variable x is formed as a mixture of two exponentials. Why? Because I'll go from reading this to that expression. How do I do that? I need lambda over lambda minus s here. So this is this is 4 over 5 times lambda 1 over lambda 1 minus s plus 1 over 5 times lambda 2 over lambda 2 minus s, where lambda 1 is 0.1, lambda 2 is 0.01. Okay? What is the associated PDF? Fx of s. Well, x is either exponential with lambda 1 with this probability, or exponential with lambda 2 with this probability. Okay? So fx of s is 4 over 5 times lambda 1 e to the minus lambda 1 x plus 1 over 5 times lambda 2 e to the minus lambda 2 x. So this is the mixture of two exponentials. Remember, I'm not adding the two exponentials. I'm not multiplying the two exponentials. I am basically randomly selecting either one of the exponentials or the other. So there's a random selection process. To form x with probability 4 over 5, I select from the distribution with rate lambda 1. With probability 1 over 5, I select from the distribution with with rate lambda 2. This way I am mixing the two distributions. Okay? So I recommend that you think about this, and in the next hour we'll address more examples of moment generating functions.